Hello, and welcome back to a video series on MAC 1105 College Algebra. My name's Sean Perry. These are guided notes number 18 in the series on Chapter 4.3, the factor and remainder theorems. Before we begin, let's review the idea of division with remainders. If I say 12 divided by 4, you probably know that's 3, with remainder 0. And because of this, we can write 12 as 4 times 3, plus 0. And likewise, this improper fraction 12 over 4 can be reduced into a whole number. Likewise, if I divide 13 by 4, we can express this as a quotient with some remainder. 4 goes into 13 3 times with 1 left over, which means that I can write 13 as 4 times 3 plus 1. And likewise, this improper fraction, 13 over 4, could be rewritten as a mixed number 3 and 1/4, where there's a little plus uniting this whole number 3 with this proper fraction 1/4. We're going to use the following theorem to figure out how to interpret polynomial division, as well as to factor larger degree polynomials. When we take and divide a polynomial p of x by a term that looks like x minus c, the remainder that we get is the exact same thing as the evaluation of p at c. In other words, the remainder is what we would get if we plugged in c into the polynomial. I'm not going to prove this theorem in this video. Suffice it to say, it is kind of surprising that we should wind up with a remainder that is the same thing as the evaluation. But perhaps it's not so surprising in light of the following corollary. Let's first note, however, that if we can write the remainder as p of c, then we have the following facts: that the polynomial p of x divided by x minus c will give me some quotient polynomial plus the remainder divided by this original divisor. This is sort of like the mixed number version of polynomial division, where we've rewritten something that's perhaps an improper fraction as a polynomial plus a proper rational, where the degree of the numerator, which is now just a number, is smaller than the degree of the divisor. Likewise, we can write the polynomial p of x as some polynomial q of x times the factor x minus c, plus the remainder p of c. And thinking about what it would look like if p of c was equal to 0 will help us understand the following corollary, or consequence, of this theorem. This is called the factor theorem, and it's really just a special case of the remainder theorem. If x minus c is a factor of p of x, then the evaluation, p of c, will give me 0. And this should be pretty clear from the definition of a factor and the zero product property. But let's see how it would look in terms of the remainder theorem. If p of c was equal to 0, then we need not write plus 0. And p of x divided by x minus c could be written as q of x, where q of x is a polynomial. Likewise, p of x could be written as x minus c times q of x, which is what it means to have x minus c as a factor. It could be written as a product with some other polynomial, and that would give me p. Now, we can see that if I were to plug in c right here, I would get 0 for p of c, because we would have some q of c times 0, and that's of course 0. What's less obvious, but nonetheless true, is that this is the only way that we can get p of c to be equal to 0. If there's some way to rewrite the polynomial as a factor, x minus c, times q of x. Let's see how we can make use of this theorem by diving into the guided notes. The first question asks us to use polynomial long division to rewrite this rational function as a quotient plus a remainder over a divisor. We would want to first recopy everything into a division symbol. We'll put our dividend inside and our divisor outside. And we'll ask, what do we need to multiply x by to get it to look like minus 6x squared? Well, we need to multiply by a minus 6 and also an x in order to get this first term to look like minus 6x squared. And then minus 6x times minus 3 is positive 18x. I like to put my x's right here because it lines up my like terms, and when I reach the end of the quotient bar, I know that I'm ready for my remainder. Now we're going to take a difference following the division algorithm This first thing gives me 0 by design, and the second thing is going to give me minus 2x. And then we drop our next term down and repeat the process. X goes into minus 2x minus 2 times. And multiplying this out, we have minus 2x and plus 6. Taking this difference, we wind up with 9, and this then becomes our remainder. We can then reinterpret this rational function as being negative 6x minus 2, a polynomial, plus some remainder, which is 9, divided by the original divisor x minus 3. These next exercises want us to use synthetic division rather than long division. Synthetic division is especially useful when we have a divisor of the form x minus c. In order to, however, correctly encode the synthetic division, we're going to need to rewrite this polynomial here in descending order. That is to say, this is really x to the fourth plus 8x to the third minus 74x minus 14. Now, what we want to do is rewrite those coefficients over here, keeping in mind that since we don't have any squares, we need to keep track of that by writing a 0 as the coefficient of the quadratic term. If there's no term visible over here, its coefficient is 0. The next thing we want to do is we want to figure out the root of this denominator. This will be equal to 0 when x is equal to minus 6. We take that number and we put it into this box right here. Now we drop this 1 down and begin the algorithm. Minus 6 times 1 is minus 6, and taking their sum we get 2. Minus 6 times 2 is minus 12, and taking their sum is minus 12. Minus 6 times minus 12 is positive 72, and taking their sum we get minus 2. Minus 2 times minus 6 is 12, and taking their sum we get positive 2. If we start out as an x to the fourth term, this is going to drop down by 1 to give me an x to the third, and we fill in the coefficients correspondingly. To write this in quotient plus remainder form, we're almost there. We just need to write plus the remainder divided by the original divisor x plus 6. Let's be careful about our signs here. This should be a minus 2, which makes this minus 2 over x plus 6. So let's repeat. Let's first go over here and encode these coefficients, minus 5, 6, and minus 8. We are dividing by x minus 1, so we have a root of 1, and we complete this division as such, dropping the minus 5 down, multiplying by 1, taking the sum, and so on. This goes down from x squared down by 1 to x, and so we'll wind up with minus 5x plus 1 minus 7 over x minus 1. Let's do this next one over here on the left to save space. I don't have any missed terms. I have thirds, squares, firsts, and constants. So let's rewrite this as 5, 36, 8, and minus 6. And now we're going to want to put minus 7 in the box. That's our root. Drop the 5 down, take the product, and we wind up with minus 35. Take the sum, we get 1, and continue. Take the product, we get minus 7, plus 8, we get positive 1. Take the product, minus 7, giving me a remainder of minus 13. This will drop down by 1 degree from x to the third to x squared. So this is going to give us 5x squared plus 1x plus 1 minus 13 over x plus 7. The next ones ask us to repeat this process, but to write it in a different form. We want to write how this factors or almost factors by writing the dividend, that's the numerator here, as divisor times quotient plus some remainder. We begin as before by encoding the coefficients for synthetic division. 1, minus 4, there are no x squareds, 3, and 1 are my coefficients. X equal to minus 1, that's our root. And we put that in the box. Drop this first one down and begin our algorithm. Minus 1 times 1 is minus 1. Take their sum is minus 5. Minus 1 times minus 5 is positive 5. Take their sum, that's 5. Minus 1 times positive 5 is negative 5. Take their sum, that's minus 2. Minus 1 times minus 2 is 2. Take their sum, that's 3. So if this began as x to the fourth, this is going to drop down to x to the third. And we would say then that x to the fourth minus 4x to the third plus 3x plus 1 is going to be equal to 1 plus x times x to the third minus 5x squared plus 5x minus 2 plus 3. For this next one, let's repeat that process. We have the coefficients 1, minus 8, 9, and 18. If I'm dividing by x minus 3, the root will be at positive 3. So we put that in this box. We drop this number down. We take 3 times that and begin. So summing, we get minus 5. Taking the product, minus 15. Summing, that's going to be negative 6. Taking the product, that's going to be negative 18. And taking the sum, we get 0. That's great. That means that x minus 3 was in fact a root of the above polynomial, which means we can take x to the third minus 8x squared plus 9x plus 18 and rewrite it as x minus 3 times the polynomial that we got as a quotient. This goes from x to the third down to x squared, so we begin with that coefficient, so 1x squared, minus 5x minus 6. Notice that now that we've dropped down by 1 degree, it's pretty easy to factor the remaining bit because it's just a quadratic. Factors of 6 with a difference of 5 are going to be 6 and 1. And so notice that the roots of the polynomial are given by 3, 6, and minus 1. This process of finding a single root, testing that by division or by the remainder theorem, and then factoring it out using synthetic or long division to get a smaller polynomial that we can factor is going to be a process that we are going to practice several times. So let's do just that. Here we are given a particular 0, which we can use to reduce this polynomial and find the factors of the remaining quotient polynomial. Notice, however, just before we begin, that factoring by grouping doesn't immediately seem to work for this particular arrangement of the polynomial. That's one of the reasons that we're doing this trick. So let's begin by synthetically dividing. We've got 1, 7, 2, and minus 40 for our coefficients. We're going to synthetically divide by minus 4, which is the root, and this will give us a reduced polynomial. Minus 4 times this is minus 4, gives me a 3, minus 12, which gives me minus 10, and then multiplying this out, we get positive 40, and that gives us a 0 remainder as desired. I mean, they told us that this was a 0, so either they lied or we're going to get a 0 remainder. That's the remainder theorem. Now, our new polynomial is going to be going down from x cubed to x squared plus 3x minus 10, and we now know that that's a factor along with x plus 4, or x minus minus 4. We can then factor the quadratic polynomial the rest of the way. We want x plus and an x minus, and we're looking for factors of 10 with a difference of 3. That's 5 and 2. Setting each one of these equal to 0 in turn gives us minus 4, minus 5, and positive 2 for my roots. So these are the solutions to the above polynomial. Here we're given a polynomial that actually, I probably wouldn't go about solving this using the last method. I mean, it really looks like this thing would factor by grouping. But just to continue on with their methodology here, let's see what would happen if we synthetically divided by 1/3, which might sound problematic, but actually look at all these numbers. They're all seemingly very much divisible by 3. So let's just give this a shot. Let's write down 36 minus 12 minus 36 plus 12 as our coefficients, and then let's put a 1/3 in the box. Now 36 drops down, a third of that is 12, and taking the sum I get 0, and putting the 0 up here, taking their sum I get minus 36, taking a third of that I get minus 12, and dropping this down I get 0. So we've gone from x cubed to x squared. And so we might be able to say that this is x minus 1/3 times 36 x squared minus 36. Now, factoring out that 36, we have x squared minus 1 here, which is the difference of 2 squares, which tells me my remaining zeros. Let's contrast this with how things would have looked if we had factored by grouping. 36 x to the third and so on. We could clearly take a 12x squared out of the first term and a minus 12 out of the second. Notice that factoring out this 3x minus 1, we still get a remainder, 12x minus 12, 12x squared minus 12, and factoring out our 12, we then get 3x minus 1 times x plus 1, x minus 1, just completing that factoring of the difference of squares. So the real difference here is that this one still has integer coefficients, while this one has rational coefficients. Notice that if I took 3 out of this 36 and put it inside, it would cancel with the 1/3 and give me 3x minus 1 here. So there's some ambiguity about what this leading coefficient out in front of the factored version should be, and whether or not we want to use whole numbers or fractions to signify those roots. Suffice it to say, you can see that these two polynomials here also have the same roots. That is to say, x is equal to 1/3 is a root of that factor and is a root of this factor as well. All right, here we have something very similar. It's another polynomial where if I was going to try this, I might try to reduce it a little bit first. But since there's a 149 here, I can't even see that everything divides by 2. Let's just proceed to see what happens when we do synthetic division by 2/5. Let's encode our coefficients. That's 60 minus 149, 110, and minus 24. And when I divide by 2/5, what are we going to get? So dropping the 60 down first, then doing my division by 5. 60 divided by 5 is 12, times 2 is 24. And then adding these two together, I'll wind up with minus 125. Now dividing this by 5, I'll get 25. And then multiplying that by 2, I'll get 50. So this would be negative 50 here. This brings down another 60, so we know this will be 24. And adding those together, we get 0, as predicted. So now we have another polynomial. This dropped from x to the third to x squared. And we know then that this factors as x minus 2/5 times 60x squared minus 125x plus 60. Now, I would definitely endeavor to reduce this first. Let's divide a 5 out of each term. And let's, in fact, multiply that 5 that we get out into this leading term. If I do all of that, I'll get 5x minus 2. And then dividing these by that 5, I'll get 12x squared minus 25x plus 12. Now, how do I complete solving this? We're either going to need to use the quadratic equation or we're going to factor. Let's try factoring first. So I'll try using the AC method here. I usually put a term in each leading place and a 1 over a out front. Then we multiply a and c, which are both 12, to give me 144. Now I'm looking through the factor list of 144 for something which has a sum of 25, which we're going to have to go a little bit farther down to find, but not perhaps so far down as 12 times 12, which would just give me 24. That's too low. So maybe just before that, what about 10? No, we have no 10s that we can pull out of 144 because there's no 5s. How about 9 then? Well, yes, we can do that. This will give me 9 times 16 is 144. And indeed, 9 plus 16 is 25. So we're going to want to put a 16 and a 9 here, and then we're going to want to reduce to get rid of this 1/12 corrective term. So we'll have 5x minus 2. Dividing out 4 from this will give me 3x minus 4. And dividing out 3 from this will give me 4x minus 3. And these terms would then cancel with the 1/12, and we're done. So now we can just set each one of these equal to 0 and solve. That's going to give me x is equal to 2/5, our original given root, plus 4 divided by 3, that's 4/3, and plus 3 divided by 4, that's 3/4. So here are our final zeros for this polynomial. Here we have one where we're looking for a repeated application of this process. We are given 2 roots, and we can therefore reduce this by 2 degrees, bringing us from a 4th degree down to a 2nd degree, which we can factor with a variety of methods. So let's set about doing just that. First, we want to take these coefficients. We have 8, 32, 38, 122, and 120, with negatives on the 38 and the minus 122. Let's put negative 5 halves into the quotient box here. Let's drop the first term down, giving me an 8. Dividing by 2 would give me 4. And multiplying that by negative 5 would give me minus 20. Taking this sum, we would get 12. Dividing by 2 gives me 6. And times negative 5 is negative 30. Taking this sum would give me negative 68. Dividing this by 2 would give me 34. And times 5 would give me 150 plus 20, that would be 170. Taking the sum here, I would get 48. And dividing by 2 would give me 24. Multiplying by negative 5 would give me minus 120, which would give me a 0 for my remainder. Now, let's just keep the party going. We know we went from x to the 4th down to x to the 3rd, but let's just not stop. Let's just divide those by a new root, which is 1. So this would be 8 dropped down times 8. Take the sum, that's 20. The product, 20. Take the sum, negative 48. And finally, we wind up with a 0 for our remainder here as well. This gives me 8x squared plus 20x minus 48, which I can't help but notice is the same thing as 4 times 2x squared plus 5x minus 12. So let's digest what we've just learned. This quartic polynomial could be factored with the following terms: x plus 5 halves, x minus 1, corresponding to our given roots. And now we've just learned there would be a 4 times 2x squared plus 5x minus 12. And that's all equal to 0. Now, we could take this 4 and kind of distribute it in here, maybe 2 of it, and distribute it in here to clean up this part, but it's not really necessary. What's necessary is to factor this thing that remains. So I'm just going to pull my 4 up front and just ignore that for a moment. The way I would factor the 2x squared plus 5x minus 12 is to put a 1/2 in front of it, a 2x in each of these two leading positions. A plus is going to go here, and then plus times a minus. 2 times 12 is going to be 24. And so we're looking through factors of 24 that have a difference of 5. 2 and 12, 3 and 8. There it is, 3 and 8. So we put an 8 here and a 3 here. If you drop this sign down, you can always put your larger number here. And then I'm going to factor out my 2 to give me x minus 4, canceling with this 1/2, and 2x minus 3. So here we have actually the completely factored version of the polynomial over the rationals, and we can use that to find the roots. So we will have roots here of 5 halves, 1, positive 4, and add the 3, divide by 2, that's 3 halves. Let's be careful with our signs. This would still be a positive, and so this would be a minus 4 actually. And our given root was actually minus 5 halves, so this would be a plus 5 halves here. Couple sign errors there. All right, moving on. When given a graph, the x-intercepts are indicating the zeros or roots of the function. And we've just learned that if we have been given roots, then we know the factors. But we don't even need to take things that far with this one, because it looks like these factors are in fact all whole numbers each. So let's take a look at how that would pertain to this situation. They're asking, when is it equal to 0? Well, they've sort of laid it out for us. It'll be when x is equal to minus 5, positive 2, or positive 4. And we could see that by doing synthetic division, but there really isn't too much of a need to take it much past this. Sometimes, however, say like the 2 and the 4 here, maybe they were just off from the 2 and the 4. Maybe they were fractions, or maybe they were irrationals. In that case, given a certain root on the number line, I could reduce this using synthetic division. So for example, if I had minus 1, 1, 22, and minus 40 here, dividing that by minus 5, dropping my minus 1 down, 5, and completing the synthetic division, we could get a reduced polynomial, negative x squared plus 6x minus 8. And factoring out a minus sign here, we could see that this actually would factor to give me the remaining 2 roots. That really wasn't necessary in this particular problem, but it might be necessary in a subsequent problem, especially if it doesn't factor and we wind up having to use something like the quadratic equation to find. the rest of the roots. Here is a great example of precisely that. We have one root, which is very visible at -2. And then we have these other two kind of mysterious roots that we don't really know even if they're rational numbers. They might not be. They might be irrational. And even if it sort of, didn't touch the x-axis and went on about its merry way, there might be some other roots to this cubic that are just complex. This is where we're going to want to factor it down to a lower degree, to a quadratic degree, and then use our various techniques to factor that and find its zeros. But what we can see for this is that f of -2 is definitely 0. And we can use that to do our synthetic division here and reduce the polynomial. We begin by setting up the coefficients. We put a -2 in the box. We drop the first one down and take its product to begin our algorithm. Taking the sum, we get 2, and so on, finding a 0 for our remainder as expected. This then gives me a corresponding factor of 12x squared plus 2x minus 2. We can try to factor this using, well, the quadratic equation would be possible, but what I'd actually prefer to do here is to reduce it a little bit more first. We could divide out everything by a 2, and let's see if this factors. Maybe it's going to have rational roots. That's possible. It's worth a check. What happens if I take 6 times 1? That's just 6. And we're now looking for factors of 6 with a difference of +1. Okay, great. That's just 2 and 3. So I could put a 3 here and a 2 here. And reducing that, we would wind up with 2x plus 1 and 3x minus 1. With our 2's and 3's canceling with this 1/6 correction term out front, this 2 kind of persists. So let's do that. Let's solve where that is equal to 0, which would be when x was equal to -1/2 minus 1 divided by 2, and plus 1 divided by 3, we'd have 1/3, which does appear to correspond pretty nicely with the roots that are given on this graph. Now, it is possible that this one wouldn't have factored, at which point we would have just gone into this expression of this quotient polynomial and used the quadratic equation. Number 13 asserts that we're only looking at a part of this graph. There may be other things going on off the edge here. We're not really looking at the whole set of roots, but we are looking at enough of the graph to discern that 7 looks like a root. So let's first encode the polynomial for synthetic division by writing down its coefficients. Let's put a 7 in this box to divide by it. And now let's drop down and begin our algorithm. 1 times 7 is 7, minus 6 is 1. 1 times 7 is 7, plus this -13 gives me a -6. And finally, 7 times -6 is -42. As desired, we get a 0 for our remainder. This gives me now x squared plus x minus 6. And we might try to factor this guy to see what the remaining roots are. X plus x minus, and now I want factors of 6 with a difference of 1. That's going to be 3 and 2. So somewhere off the edge of this map, we have the following roots. X is equal to -3, and x is equal to +2. We should combine that with the given root of 7 to complete the problem. In the same way, this last one we should have included -2, the given root. Alrighty, that's going to do it for this video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.